And we can begin. Hello, everyone. My name is Sarah McAnulty. I run the Skype a Scientist program. I'm also a squid biologist, and I'll be moderating this session today. Let me see if KJ is here. KJ is our ASL interpreter. Looking like no, but we'll use the transcript. I hope that's okay for everybody. Okay, so at this point, thank you, first of all, Noel, thank you so much for joining us today and talking to us all about earthquakes and volcanoes and all this stuff. We're really excited to hear about it.
Sure. Would you like me to introduce myself?
Oh yeah, I'll hand it over to you, and then you can do your intro spiel. That would be wonderful. Thank you.
Sure. All right. Hi, everybody. Thanks for joining us. I am Dr. Noel M Bartlow, and I am a professor of geophysics at the University of Kansas. Geophysics is an interdisciplinary field that combines geology and physics. So I'll just tell you really briefly how I got here. I went to a math and science, a public magnet school in Maryland, and then for high school. And after that, I went off to Carnegie Mellon University, where I got a bachelor's degree in physics. And after that, I went to a PhD program in geophysics at Stanford University, which I completed in 2013. So I have a bachelor's degree in physics and a PhD in geophysics. And then I've hopped around a bit, and I'm now currently, as I said, a professor of geophysics in the Department of Geology at the University of Kansas. Most of what I do these days is study faults, geologic faults that produce giant earthquakes. We call them megathrust earthquakes is actually the technical term. And the giant earthquakes also produce tsunamis. They're a major sort of hazard for people who live on coasts near the certain type of fault that produces these earthquakes. And I study them using GPS. It's the same GPS that might be in your phone or your parents' phone that they might use to navigate. We can actually use GPS to study earthquakes. And I also go to sea during the summers on ships. And I tell my family I go to sea and throw expensive electronics overboard, which it's true that actually we use a specialized crane to drop expensive electronics overboard and plant them on the seafloor to study underwater fault motions. So that's most of what I do. I'm an expert in everything plate tectonics, earthquakes, and also volcanoes. So that's my introduction. And I teach classes here at the University of Kansas at the undergraduate and graduate level, and I run a research group supervising graduate students and doing various types of experiments and data analysis related to earthquakes and plate tectonics.
Very cool.
So yeah.
Awesome. What a cool job. So I'm a squid biologist. I've never been to sea. I would love to go to sea. It's on my bucket list big time. Okay, let's get into these questions. We've got a question from the Ruiz Blanco classroom. Have you ever been to a volcano?
I have, in fact. I've been to numerous volcanoes. So the only volcano that I have actually seen erupt was Volcan Arenal, which is in Costa Rica. And that's a volcano that erupts frequently, and it's a nice sort of cone-shaped mountain. It's the volcano you're thinking of that has nice little dribbly lava down the side. But, I get a lot of volcano questions, and it's important to know that volcanoes don't always look like you think they do, like a nice mountain. Sometimes volcanoes aren't even mountains. So another volcano I've been to is Lake Taupo, which is in New Zealand, and as you might gather from the name, is in fact a lake. So that's a type of volcano where you have a giant magma chamber underground, and when the volcano erupts, the magma chamber acts like a deflating balloon. It shrinks, and the ground on top of it sinks down because of the deflating magma chamber balloon below it, creating an indentation that then fills with water and becomes a lake. So sometimes volcanoes look like lakes. This is called a caldera volcano. Another example of a caldera volcano is actually Yellowstone, which is a volcano that is an indentation in the ground. That's another one that I've actually been to as well. So those are 3 volcanoes that I've visited. Oh, and also Kilauea, which is on the big island of Hawaii. I've been to that one as well.
Awesome. Very cool. All right. The next question is, what is the biggest earthquake and/or volcano that you've ever recorded?
Yeah, so actually in my field, most of the data is shared between scientists. So when I'm going to interpret that question as the you being us geophysicists collectively, as opposed to me personally, the largest earthquake recorded by modern seismic instrumentation is a magnitude 9.5 earthquake that occurred in Chile in 1965. But maybe a better answer to that question would be like the largest earthquake I've ever actually felt or been in myself, which was a magnitude 7 earthquake in New Zealand. I do a lot of work in New Zealand, and I'm really lucky that I've been able to travel there 3 times now for various work reasons. But as somebody who studies earthquakes, I tend to travel to places that have earthquakes and sometimes get actually, experience those earthquakes. So a magnitude 7 earthquake in New Zealand, which gave us a good shake. I was doing what you're supposed to do in an earthquake, which is we teach people to duck, cover, and hold on. So you want to get underneath a piece of furniture, ideally a table or a desk, and then hold on to the legs of that piece of furniture. And this is to protect you from anything that might fall, like if a lighting fixture or a piece of art were to fall off the wall or a bookshelf were to fall over, you're going to be protected. And so I was doing that procedure, duck, cover, and hold on, and everybody was fine.
Great. So one of our questions was, how do you survive an earthquake? So I think you just answered that one, duck, cover, and hold on. How do you survive a volcano eruption?
Oh, that depends a lot on the specifics of the eruption. So there's a wide variety of volcanoes. As I sort of already described, there's the kind that look like mountains and the kind that look like lakes. And of the kind that look like mountains, there's the sort of tall, steep mountains, and then there's the sort of wide, broad ones that you get in Hawaii. And the different types of volcanoes produce different types of eruptions. Some of them are sort of slow and dribbly, and some of them are big and explosive. And it really just depends on the type of eruption, but mainly the thing is to leave the area. Get as far away as you can as quickly as possible is going to be the main advice for an explosive volcanic eruption.
Sounds good. All right, next we've got a question from Matt. Do you study underwater seismic activity?
I absolutely do. Yeah, that's actually one of my specialties, and that's why I go to sea during the summers. And there's actually multiple ways to study underwater seismic activity. We use seismometers, which some people may have heard of seismometers, and those can record underwater earthquakes even if the seismometers are placed on land. But we also have underwater seismometers that can do an even better job. My expertise or the type of instrument that I use is actually not seismometers. It's a type of underwater instrument that combines GPS and also sonar. It's a bit technical to explain, I think, here, but it combines GPS and sonar to record very, very small motions underwater that we think might tell us where future earthquakes are going to occur. So yes, both we as a field study underwater earthquakes, and I personally do it as well.
Are those instruments like sitting on the seafloor, or are they floating around?
Yeah, they sit on the seafloor. In fact, I can show you some pictures.
Oh, cool. Yeah, let's check it out. That'd be cool.
Yeah, hang on. Yeah, this is a photo album from my expedition last summer. And we used the underwater robot Jason to deploy instruments. So here's some pictures of me with Jason. But Jason itself takes some pictures of the instruments underwater. So in fact, here's a good one. This is one of our instruments sitting on a concrete base, sitting on the seafloor, and the part that says D equals 1533, that's indicating that this is at a depth of 1,533 meters underwater. So this is what one of our instruments looks like.
Wow, super cool. Here's another instrument related question. Does the equipment that you throw overboard ever break, and what would happen if it did?
Oh, yes, it does. Yeah, that's an excellent question. I'm actually trying to figure out how to stop sharing my screen, but in the meantime, you can still see some of these pictures. Yes, that does occur, especially with underwater instruments are risky, and yes, they can break. So we try to mitigate that. We try to repair them. In fact, one of our instruments this past summer, we installed it on the seafloor. It wasn't working. We ended up sending Jason down to pull the instrument up. We pulled it back on the ship and we repaired it and we put it back down there. So sometimes we can repair the instrument, sometimes we can't, and we just have to replace it. But, we do our best, but these experiments are risky, and occasionally, failures do occur. But for the most part, the instruments operate as expected.
Cool. Sounds good. The next question is from Sarah from room 27. Can an underwater volcano erupt?
Yes, absolutely. All right. Sorry, I'm still trying to figure out how to stop sharing my screen.
I might be able
Which
to
I-
stop it for you. That should do
Oh,
it.
there we go. Excellent. Yes, underwater volcanoes absolutely can and do erupt. And in fact, when they do that, we have volcanoes that are completely underwater, and some volcanoes where the tip, the very peak of the volcano, may be above the water, but part of the volcano is underwater. And when volcanoes erupt underwater, a bunch of different things can happen. One thing that can happen is it can generate a tsunami. So a tsunami is just a very large wave that is generated whenever you have large movements of mass of the ground underwater. And so sometimes when volcanoes erupt, there's landslides, or just the force of the eruption itself can generate tsunamis. Another thing that can happen with underwater eruptions, if they're in shallow water, is they can cause steam explosions. So the lava is very, very hot, and it causes water to very quickly go from liquid to steam, the gaseous form. And that comes with a huge expansion, and that can cause explosions. But if underwater volcanoes erupt at the bottom of the ocean in very, very deep water, which is actually a common occurrence, there's a line of volcanoes, for example, in the middle of the Atlantic Ocean that erupts all the time. And if it erupts at the bottom of the ocean, there's so much pressure. So if you've ever been in a swimming pool and gone to the bottom of the pool and maybe your ears popped, then you know that as you go deeper in water, the pressure increases. And when you go all the way to the bottom of the ocean, the pressure is so high that it prevents any explosions from happening. And you just get these kind of happy looking eruptions where the lava comes out and makes these sort of bubbly shapes. And we actually call them pillow lavas because they end up sort of looking like a pile of fluffy pillows. And it's completely not dangerous at all.
Cool. Sounds good. Our next question is from Aziz. How accurate is the technology that helps us forecast future earthquakes?
Oh, that's an excellent question. And I love that the person that asked that question used the word forecast, because we like the word forecast better than the word prediction. So where our current technology is at right now with earthquake forecasting, I guess there's sort of two ways I could interpret that question, but our forecasts are typically given as probabilities of exceeding some sort of shaking threshold over some amount of time. It's the amount of time is usually 30 or 50 years. And so we're actually not very good in the kind of shorter timescales at forecasting earthquakes, but we're pretty good when it comes to the 30 to 50 year timescale, which is what we need in order to, say, build a new building. So if you're building a new building and your engineer needs to know how big an earthquake does this building need to survive, and I'm trying to build a building that lasts 50 years, then that's the kind of information that they need. And so we have these hazard maps that usually say things like, for a 50-year design, you need to design for, it's usually given as a % of acceleration of gravity. So you might need to design a building that can withstand shaking that's half as strong as gravity, or that kind of thing. Those, I mean, as far as how accurate they are, it's hard to know because you have to wait 50 years. But I think those kinds of things are pretty accurate. The other way I could go with that question is the actual instruments that go into the modeling. So like the GPS instruments that go into that modeling are accurate to about 2 millimeters. And yeah, I can't quote the accuracy of the seismometers off the top of my head, but they're extremely accurate.
Amazing. Really cool. All right, we got a question from the Braun classroom. We are doing a sound inquiry unit right now in 2nd grade, and we're wondering, how do sound waves and vibrations affect your job, and what we
you know what, there is a great connection there. So sound waves and seismic waves are basically the same thing, except that there's only one kind of sound wave and there are 2 types of seismic waves, but one of those types of seismic waves is the same as a sound wave. So what a sound wave is a pressure wave. And what a sound wave is, right, it's alternating areas of high and low pressure in air that travel away from you. And in fact, we teach this to our college students using a slinky, right? And so a sound wave is sort of like this. It's a compressional motion of the slinky. In the earth, we can also get shearing motions that look like this, side-to-side motions. That's the other type of seismic wave, and there is no sound wave equivalent to that one. But essentially sound waves and seismic waves are essentially the same thing. So when you get, and by the way, what I mean by seismic wave, you get an earthquake occurs, and an earthquake is typically slip on a fault, so a geologic fault that moves suddenly, and that it's kind of like a loud boom goes off in the earth, and the waves travel away from it just like sound waves would travel away from an explosion, and the waves carry the shaking. So when you actually experience shaking from an earthquake, you are experiencing the seismic wave itself, which is effectively a sound wave that traveled through the earth.
Super cool. All right, we got a question about your roots. When did you originally start getting into science?
Honestly, I don't remember not being into science. I was a space nerd as a kid. You know, I loved all things outer space, and was obsessed with like the Hubble telescope and stuff like that. So I was a space nerd as a kid. It wasn't until college that I started getting into natural disaster science, which is where I ended up. But yeah, I've always been fascinated by science. So yeah, forever.
Sounds good. But I have a lot of friends, just like as background, I have a bunch of friends who are scientists who didn't know what they wanted to do until like way later. So if you don't know you like science yet, I also, much like Noel, liked squid from when I was very small, but like Noel and I are not, all scientists didn't like things from when we were very small. So, you know, it's like the actual working scientists are all different ranges of when they got into it. So I just like to say that as a disclaimer.
That is true. Yes.
Yeah.
You
Yeah.
know, I'm one person. Yeah.
Yeah, and I'm also just one person, but there's so many of us that have so many different paths to science. Our next question is, how many earthquakes happen each day? That's from Luke in grade 7.
Oh, well, an uncountably high number, to be totally honest with you. So earthquakes come on a magnitude scale, which you might have heard of. And for those of you who might have already gotten to logarithms, which I expect many of them have not, but they come on a logarithmic scale. And what that means is that for every unit that you go down on the magnitude scale, you're actually going down a factor of 10 in the amount of energy released. So like a magnitude 7 releases 10 times more shaking than a magnitude 6, which is 10 times more shaking than a magnitude 5, and on down the scale. But as you go down, the amount of shaking goes down by these factors of 10, but the amount of earthquakes that we have goes up by factors of 10. So we have 10 times as many magnitude 4s as we have magnitude 5s, and 10 times as many magnitude 3s as we have magnitude 4s. And our instruments can register earthquakes down to about magnitude 2 reliably, and occasionally in some special circumstances to smaller magnitudes. But a magnitude 2 earthquake would be way too small for humans to feel, but our instruments can feel them. So if by earthquakes you mean the ones that we can record on our instruments, it's many thousands every day. If you mean the ones that humans can actually feel, that would probably be between 10 and 50 per day, roughly.
That's still so many earthquakes. That's
yes,
wild.
they're constantly happening.
Wow, so cool. All right, our next question is from Mrs. Rice's class. Do any animals live on a volcano?
Sure, yeah. I'm not a biologist, but yes, absolutely. So some examples that come to mind is there's a bunch of volcanoes in the Pacific Northwest, and you know the sides of the volcano will be forested, and you'll have your typical forest creatures. Another excellent example related to the underwater volcano question from before, those deep water underwater volcanoes that produce those sort of piles of pillow happy looking lavas, they're not violent, they're not explosive, but they produce a lot of heat, and they can produce something called a hydrothermal vent underwater, which is an area where hot water is coming up. And those hydrothermal vents are absolutely rife with sea life. So there's actually a link between underwater volcanoes and sea life. In fact, a lot of underwater animals seek them out for heat.
For sure. The hydrothermal vents are so cool.
Yeah.
The next question, could you just like basically explain what exactly a geologic fault is?
Yeah, absolutely. So a geologic fault, the best way to think of it is a crack in the earth. And that's effectively what it is. So if you think of, so the earth has layers, and we live on the top layer, which is called the crust. And the crust is essentially made of solid rock. And then there's above that, there's, you know, depending on where you live, there might be things like soil and plants. But if you dig down beneath the plants in the soil, eventually you will hit solid rock. We call that bedrock. And then that top layer of the earth, the crust, is all made of essentially solid rock, but there are cracks in that solid rock. And those cracks are essentially faults. And the other technical part of the definition of a fault is that the two sides of the crack have to move relative to one another. So if you have a crack and there's any sort of motion of the two sides, then it's a fault. And earthquakes occur when faults move very suddenly.
Very cool. All right. Next question is from the ecologist school in Houston. How do super volcanoes form?
Oh, yeah, that's a great question. So as I mentioned, there are different types of volcanoes. And I mentioned that lake in New Zealand called Lake Taupo, and I mentioned Yellowstone. Those are both considered supervolcanoes, and they're the sort of sunken down dent in the earth that gets filled with a lake often type. And how those form, I've sort of already given part of the answer that there's this huge magma chamber that when it erupts collapses and that kind of thing. But why is there such a huge amount of magma under there that makes the supervolcano? That actually has to do with the Earth's mantle, which is the layer beneath the crust. And what happens is very, very hot rock from the mantle, from the bottom of the mantle, comes up in a jet of hot rock through the mantle. We call this a mantle plume. And that jet of hot rock hits the base of the crust and starts melting and building up that melt. And that melt eventually bursts through the bottom of the crust and forms a magma chamber sort of in the middle of that crust layer that we live on. And that forms the supervolcano. So mantle plumes essentially is your answer there.
Mantle plumes.
It's a little bit kind of like a lava lamp.
Like a lava lamp in a national park. Beautiful. Sounds good. We've had a couple questions that are basically circling around, like, what is the coolest experience you've ever had as a scientist?
Ooh. Actually, it might have been my sea expedition that I was briefly showing photos of from last summer. I got to see whales and dolphins, and I'm not a biologist, but I think what made that experience really cool for me personally, without getting too technical in the details, I have that expedition was off the coast of Oregon, and we were studying a very large fault out there called the Cascadia subduction zone, which can produce very large earthquakes that sort of threaten the Pacific Northwest region in the United States. And I'm very interested in trying to learn more about that type of earthquake. And I have a very particular hypothesis that, I'm hoping I'm right, but it's a little bit of a high risk science project. And I convinced the National Science Foundation to fund this project whereby I teamed up with an engineer from another university who invented a whole new type of instrument that involves a laser and a robot and costs $1 million. And the National Science Foundation paid for the engineer to build 2 of these instruments just for me. And then we all went out on a ship and put them on the sea floor. And it's all just to test my idea. And, I got to watch the robot install the instrument. And it was just like amazing to get to see something that started as an idea in my head go all the way to an entire team of engineers on a ship installing $1 million worth of equipment just to test to see if my idea is right. By the way, we don't know the answer yet. So we have to wait until next year to get the data. But
That's so
that
cool.
was an amazing experience. Yeah.
Amazing. All right, we've got another question about your tools. What happens if an animal eats your underwater tool or if it gets covered in sand? And is that like a problem? I know there's this one picture of like a bunch of sharks chomping on something. Like what's that about?
Sure, yeah. For the most part, animals are not a big problem for us. We actually will record them on our instruments, but we're pretty good at getting rid of those and not, we can tell the difference between an animal and the type of signal we're looking for. At that deep sea level where we're installing things, the types of animals that we're encountering out there are not a real problem for our instruments. There's no large sharks that are going to come chomp on our instruments. And also our instruments are maybe bigger than you think they are. They weigh like 1,000 pounds. So we're too concerned about animals. However, the human animal is actually an issue. And so human fishermen there's a type of fishing called trawling where they literally just scrape the bottom of the ocean and they will trawl right over our instruments and that will cause damage. So it actually means that we can't deploy our instruments in areas where trawling fishing occurs, and we have to choose our instrument deployment locations to avoid that. As far as sand, so yeah, at the bottom of the ocean, there is something called marine snow, which is mostly biological material, and our biologists might know more about it, that's constantly falling. And so that marine snow does coat our instruments. This is actually okay for our instruments. And in fact, a lot of times we try to bury our instruments in that goop that's at the bottom of the ocean because we're trying to record what the rocks are doing and not what the ocean above is doing. And so anything that kind of cushions us from stuff going on in the ocean above is actually a good thing.
Very cool. Yeah, marine snow is super interesting, but we could talk about that forever. That's not what we're talking about today. So here's an interesting question. How do volcanoes stay warm underwater?
Yeah, okay. So volcanoes, regardless of what type of volcano it is, volcanoes are fed from below. And they're fed by some kind of hot process, usually in the Earth's mantle, that layer below the crust that causes melting. And that hot molten rock underneath the volcano is always going to keep it warm. So even though it might have like water or air cooling it from above, it's always getting heated from below. And actually, you know, one thing that is important to get across related to volcanoes, even if it wasn't quite what this person asked, is that a lot of people have the misconception that the mantle, that layer below the crust, is all molten melted rock. It's actually not. It is solid. The mantle is solid all the way through, but there are certain processes that would take me a long time to teach. We teach them in our college level classes, but there are certain physical and chemical processes by which the mantle interacts with the crust in certain ways that can cause melting to occur. And when melting occurs, that melted rock is buoyant. It's the same. It basically wants to float on top of the solid rock. And so eventually it will make its way up to the surface and become a volcano. So anyway, the volcanoes are heated from below.
Very cool. Sounds good. All right. Our next question is from Scarlett from Pawtucket. Scarlett would like to know, how long in between or after a volcano erupts will it take for it to erupt again? And does it depend on the area or the volcano?
Yeah, it depends mostly on the type of volcano and how large the eruption was. So just in the same way that the smaller earthquakes happen more frequently, smaller volcanic eruptions happen more frequently as well. So sometimes a volcanic eruption sort of won't relieve all the pressure on the volcano, and there'll be some pressure left over, and then a future eruption could happen pretty soon. In that case, it's sort of really more of a second phase of the first eruption. And so sometimes we get kind of back-to-back eruptions because it's just kind of a multi-phase thing as relieving the pressure in the volcano. Once you have kind of relieved all that pressure in the volcano, it takes a while for that to build up again. For the types of volcanoes that we have, say, in the Pacific Northwest, it would be every few hundred years for major eruptions for those. For something like Yellowstone or a massive supervolcano, it's going to be anywhere between like 100,000 years and 1,000,000 years. So a really, really long time. So the larger the eruption, the longer it takes to build up that pressure again.
Sounds good. Very cool. A lot of folks want to know, like, how do you know if a volcano is about to erupt?
Yeah, sometimes they erupt without warning, but most of the time they actually don't. And again, the larger eruptions give us more warning than the smaller eruptions. So what do I mean by warning? So as the eruption is kind of getting ready to happen, what happens is that magma has to start moving around underground to try to make its way to the surface to erupt. And as it starts moving around underground, it's going to start shifting rocks, and those shifting rocks will be recorded as earthquakes. So we'll actually see a bunch of earthquakes occur on or near the volcano before the eruption occurs. We might also, in the case of Mount St. Helens, which these students may or may not have heard of, but this is a volcano in Oregon that erupted in 1980. No, actually it's in Washington, isn't it? It erupted in 1980. And in that case, this is sort of one of those like nice triangle mountain volcanoes. As the magma was working its way up the volcano, instead of going out the top, it actually started to come and veer out the side, and the side of the volcano started growing a big bulge, like a big pimple on the side of the volcano. And scientists were actually monitoring that bulge growth at the time. So we'll see earthquakes. We might see the volcano itself start to bulge in certain regions or change shape. And occasionally we'll start to see certain types of gases like CO2 or actually some poisonous sulfuric acid type stuff come out of volcanoes prior to eruptions.
Very cool. Could you give us like a general overview of like what are the different types of volcanoes? Like you mentioned, there's cones and etc.
Yeah, I think I might have a picture pulled up for that, or maybe I don't actually. Sure. Yeah. So Okay, the three main types of big volcanoes, we've actually sort of already talked about them. There's the ones that are like basically indentation lakes.
Right.
Those are called calderas. Then there's sort of the nice happy triangle kind you're used to. Those have a couple different ways, names. They're called stratovolcanoes or composite volcanoes. And the way that those form, they actually form in conjunction with something called a subduction zone, which is where we haven't really talked about tectonic plates, but a tectonic plate sinks into the earth and is destroyed. And in that sinking process, there's some chemical reactions that occur that cause melting, and the melt comes back up, and it's associated with these lines of pretty triangle mountain-shaped volcanoes. Mount Fuji in Japan is a good example of that type. Another type of volcano that students are probably familiar with is the Hawaiian type. Those are called shield volcanoes. They're called shield volcanoes because they, instead of being like a tall mountain like this, they're a real broad mountain. They're actually even taller mountains, but they're just really, really wide mountains. And so they sort of look like a shield turned on its side. Those are actually formed in a very similar to way to how the caldera volcanoes are formed. They're hotspot volcanoes, meaning that they come from this mantle plume that comes way through the, deep in the mantle. And those are actually really interesting because you can get a chain of volcanoes. I actually do have a picture for that, I think, maybe somewhere. So what happens is, yes, I do. Let me share my screen real quick. Yeah. So for, oops. This type of volcano, here's a picture of a mantle plume, and you have this tectonic plate that moves on top of the mantle plume. So as the mantle plume is coming up, the tectonic plate moves on top of it, and it results in a line of volcanoes that as the tectonic plate moves over the mantle plume, every so often the mantle plume melt material kind of pokes through and creates a volcano. So you get this chain of volcanoes, and that actually is how the Hawaiian Islands formed. So that's another type of volcano. Beyond that, those are sort of the three main types of really large volcanoes. There's a bunch of other types of volcanoes that are smaller, such as volcanic fissures, which are basically cracks in the ground that erupt, or cinder cones, which are really, really tiny volcanoes that are just made of a pile of basically volcanic material. Those are your main types.
Very cool. Thank you. Our next question is from Becca in Mrs. Bolt's 7th grade class. What other kinds of scientists do you work with, and how do they help your field?
Oh, sure. Yeah. Can you do the stop sharing for me?
You bet. Yeah.
Yeah. So earth sciences are very interdisciplinary. And actually, it's sort of a personal gripe of mine, how little attention earth sciences get in especially the high school level. For most students, they might take earth sciences in middle school and then not again ever, which is kind of sad, I think, because it doesn't get as much attention as some of the core sciences like physics, chemistry, or biology. But earth sciences is actually extremely interdisciplinary. And I work with, like myself, I have training in both geology and physics to do my work. But then I work with other scientists all the time. So a type of scientist that I work with frequently is what we call a petrologist. And a petrologist is somebody who's interdisciplinary between chemistry and geology. So I understand the physics behind the geological processes, but I'm not so good at the chemistry, but the chemistry and the physics work together. So a lot of times the physical processes are driven by chemical reactions or phase changes that are occurring deep within the earth, or chemical reactions that often involve water are important. So in our field, we need a lot of interdisciplinary knowledge, and we do have to work together. I also work with engineers frequently. So as I described my expedition this past summer, in order to test my scientific hypothesis, I needed an entirely new type of instrument that had to be designed and built by a specialty engineer. So I work with engineers as well to design and build the instruments that we need to make the measurements that we need.
Awesome. Sounds good. Our next question, how many years have you been researching volcanoes and earthquakes?
So I finished my undergraduate degree in December of 2007 and started my doctoral studies in September 2008. And that was when I switched fields. I was majoring in astrophysics as an undergrad, and I switched to geophysics from graduate school. So if we start there, then since 2008, so 14 years.
Nice.
But
Sounds
it's
good.
been 9 years since I completed my doctorate.
Cool. Our next question is, are there any volcanoes that can shoot water?
Sort of, yes. Not directly, but you're actually familiar with one probably already. So if you've ever heard of Old Faithful, the geyser at Yellowstone, that Yellowstone is a volcano, and the reason that there's a geyser there is because the water gets heated by the magma underground, and then the pressure builds up in the hot water, and then it shoots out of the ground. The magma and the water actually never touch each other. The heat is transferred through rocks. They never touch each other. But so volcanoes don't directly erupt water, but they can cause water that is already underground to get so hot that it then bursts out of the ground in a geyser.
Sounds good. Our next question is from Nico in Orac Forest, Illinois. What's the strongest earthquake that you've ever personally felt?
Yeah, I actually sort of already answered that question. It was a magnitude 7 earthquake in New Zealand. I've
Sweet.
only felt, so I'm from the East Coast originally, and I've only felt, I think, 4 earthquakes in my entire life.
I felt 0 earthquakes in my entire life. So
yeah,
yeah.
and I felt my very first earthquake after I'd been studying them for 4 years. So not that many. And now I live in Kansas. We don't have many earthquakes in Kansas. Now, it used to be that we didn't have any. Now it's that we don't have many, because we do have them now.
Because of fracking, or?
Yes, because of wastewater injection related to fracking. They're man-made, yeah.
Whoops. Sounds good. All right, our next, we've had a couple questions about tsunamis. Do you want to kind of go over how those happen and what to do if you think a tsunami is coming?
Sure. Yeah, for sure. So tsunamis are generated by any kind of process that moves large amounts of rock underwater very quickly. And essentially that boils down to 2 things, volcanoes and earthquakes. So they can be triggered by underwater earthquakes or underwater volcanic eruptions. The largest tsunamis are triggered by underwater earthquakes. Those are the really dangerous ones. And I don't know if any of the students would be familiar with this event, but in 2011, so 11 years ago now, there was a massive underwater earthquake off the coast of Japan, and it triggered a huge tsunami, and the tsunami hit a nuclear power plant and caused a nuclear disaster. So, okay, so that's how tsunamis are generated and why they can be terrible. So what actually is it? Well, a tsunami actually doesn't look like it looks in the movies in reality. So they are very, very large waves. Essentially what happens is, if you think of, you've got the sea floor and the sea surface, you move the sea floor very quickly and it moves the sea surface, and then that bump in the sea surface travels away as a wave. That's what happens. Well, they are in fact very, very tall waves, but they're what the movies don't show you is they're also very, very wide waves. In fact, they're much wider than they are tall. So if you were to see a tsunami, it wouldn't even look like a wave to you because of how wide it is. What it actually looks like, if you're standing on a beach and a tsunami arrives, it looks like one of 2 things. It depends on whether you get a negative wave arrival first or a positive wave arrival first. If you get a negative wave arrival first, it'll look like the water pulling out, like the water level goes down and the ocean pulls away from the shore, like way, way lower down than low tide. It just keeps going out, keeps going out, keeps going out. And it comes with a very strong current because the water is whooshing out to the ocean. And then it'll all come sloshing back and then some with a huge current, again, pushing the water inland. And the other thing that can happen is that the positive wave arrival comes first, in which case you don't get the draw out first, you just get the water rushing in. So it just looks like water rushing in, rushing in, rushing in, water level getting higher and higher, higher, very strong current. And that can go on for 10 or 15 minutes. So it's extremely destructive, and it is a wave, but it doesn't actually look like a wave. So if you see a movie where it's like a big wall of water, that generally is not actually what tsunamis look like. So in fact, what should you do? So tsunamis are extremely destructive and extremely deadly. If you get caught in one, it's unlikely that you'll survive. However, it is very survivable because you can escape tsunamis pretty easily. So we now have pretty good tsunami detection and warning systems. And even in the case of, say, the Japanese earthquake, the tsunami was very survivable because there's about 10 minutes between when the earthquake occurs and when the tsunami hits. And they have a lot of high-rise buildings that's long enough. So we call this vertical evacuation. So if you're ever at the coast and you feel a large earthquake, what a tsunami may or may not have been generated, but if you don't know, assume that one was, and your goal is to get as high as possible, as quickly as possible. So if you can get at least 3 stories up, you will be safe. So we call that vertical evacuation. So go for high ground or go for a 3-story or taller building are your general safety measures. Tsunamis can have deadly impacts all the way across oceans. So the Japanese tsunami caused damage in Hawaii, for example. But it takes many hours to travel across the ocean. So there's plenty of time to warn people, thankfully.
Yeah, I'll never forget those images of Japan after that tsunami. That was wild. They're burned into my memory forever.
So vertical evacuation.
Yes, evacuation is good. All right, we are almost at time, but I want to ask one more question. And we're just going to pick randomly because there are 233 questions in here. Folks, I just want to make sure everybody knows, if you want your own volcanologist to talk to your classroom individually, we always have that available for you for free too. So if you're like, at the end of the session, I have 15 more questions, just sign up for a session and we'll give it to you for free. Okay, but here's the last one. Why does Iceland have so many volcanoes?
Because it's a hot spot.
It's a hot
So
spot.
there's a mantle plume underneath Iceland, similar to the mantle plume that's underneath Hawaii. Sorry, that was a short answer, but that's why.
That's why. Well, that's good. That's fine. I'm gonna post the link so that if you want to have your own volcano earthquake session in your class, in addition to this at any point, maybe even next year, whenever you want, you can fill out that Google form. You can of course, always find that form that's up to date for the semester that we're in at skypeascientist.com. But now I'm going to ask you the same 2 questions that we end every session with. The first is, you have everyone's attention in the whole world. You can tell them one thing related to your area of expertise. What do you tell them?
Yeah, I actually thought about this ahead of time, and I've sort of already said my answer, which is that I wish that we had more emphasis on earth sciences in our educational system at all levels, actually, because earth sciences are, I think, vitally important. You know, we all live on this planet, and we're all subject to the hazards of this planet. And I think it kind of gets it sort of gets put last. And I think in the basic sciences for a lot of people, and especially, you know, I was a scientifically minded student quite young, as we discussed, and it didn't occur to me to study earth sciences until after I had finished my college degree. I never even thought about it. So I guess that's kind of a message I'd like to get out there, is that, you know, don't, if you're interested in science, think about the earth sciences. It's interdisciplinary. We need chemists, we need physicists, we need engineers. We use plenty of math, but then if you hate math and you still love science, there's plenty of biologists in earth science who don't use any math. So we need all kinds. We're very interdisciplinary, we're very broad, and we work on understanding problems of huge societal relevance. So don't ignore the
Great answer. Very good. All right. You still have everyone's attention in the world. You can tell them one thing not related to your area of expertise. What do you tell them?
Okay. I wrote down an answer to this question. So bear with me here. I think this is a good message to give, you know, honestly, children and adults, everybody. But the most important thing you'll ever do in your life is figure out how to be happy. And that sounds really easy, but it's actually very, very difficult. And it's something that most people work on for their entire lives. Because in order to be happy, you have to figure out what's important to you. And that's not what's important to your parents, and it's not what's important to your friends. It's what's important to you. And so is it important to you that you do a job that makes an impact in the world? And what does impact mean to you? Is it important to you that you get to follow your curiosity? Or is it more important to you that you follow directions given by other people? Is maximizing your free time important to you? And these are all things that you have to figure out in order to make decisions about how you're going to live your life in a way that will make you happy. All decisions, all life paths involve sacrifice. And if you know what's important to you and you're making decisions based on that, then you won't mind the sacrifices that come with it. So most adults that look like they know what they're doing are still trying to figure this out as well. Everybody works on trying to figure out how to live life according to their own values and the ways that make them happy. It's something that most people work on for their entire lives. So start thinking about it now.
Great answer. Well prepared. Wonderful. Thank you so much. Thank you for sharing all this knowledge with us today. This has been really, really cool to learn about. Is there anything else you want to plug? Anything else you want to share before we wrap up?
I'll just share like a general message that I always give when I talk to classrooms full of students, which is that science is about curiosity. The best part of my job is that I get to follow my curiosity. And it's also about creativity. You know, what I do as a scientist, what all scientists do, our goal is to learn things that nobody has ever learned before. It's sort of the definition of science. You're trying to learn something that no one's ever learned before. So when you're in school and you're doing science, you're probably following instructions, you know, do this step, then do this step, then record what you got, then do this step. But practicing scientists don't have instructions anymore. We have to be creative. We have to figure it out for ourselves. There's a lot of trial and error. There's a lot of failure. But when you discover something that nobody's discovered before, it's the best feeling in the world. So keep following your curiosity and remember that being curious is more important than being right.
That's great. So true. All right. Thank you again. Thank you everyone for joining us. We will be back at it talking about brain chemistry on the 29th of November. We got 2 more sessions this semester, that and then robotics in December. We will see you next time. Thanks for coming. Bye.
Thanks, everybody.